I'm Hitesh Ballani. I'm a researcher at Microsoft. And today I'm going to tell you about how we're using light and optics to reimagine the future of our cloud network as we approach the tail end of Moore's Law. Now, historically, the power consumed by the network in a typical data center has been around 5% of the total data center power. So it's an important number, but not something that we lose sleep over. However, that may be about to change because of new applications and new scenarios that are putting a lot of pressure on the underlying network. A very good example is large-scale machine learning. The size of the models that we've been trying to train has been growing by more than 10 times every year, which is much faster than the gains that we are even getting because of Moore's Law. Actually, since 2019, the size of the largest model has exceeded the amount of high-speed memory available on individual training devices. So we have to train these models in a distributed fashion, which means communication across the network during the training phase, which in turn necessitates the need for an ultra-high bandwidth network. If you look at all the recent AI training devices on the market, the off-package bandwidth here in all these cases is more than a terabit per second, which is more than 10 times higher than the bandwidth available on a typical cloud server today. And it's not just machine learning. Trends like resource disaggregation and increasing use of hardware accelerators all require a step change in network performance in terms of bandwidth, and in some cases in terms of latency and reliability. And it's very hard to achieve this step change with incremental changes to traditional networking technologies. So if we go back to our power analysis, yes, historically, the network has consumed 5% of the total data center power. And as we look ahead to servers being equipped with 200 gigabit per second and 400 gig network bandwidth, this power will start increasing gradually. But the real worry here is that if I want to build an AI supercomputer comprising tens of thousands of AI accelerators with more than a terabit per endpoint network bandwidth, the power consumed by the network inflates to about 50% of the total infrastructure power, which is of course not sustainable from an economical or from an environmental perspective. And this is the real power wall and the associated cost wall that we are very worried about. Now, if we were to break this down, the cloud network today comprises of two main components: electrical switches and transceivers that take digital data and encode that into light waves that are transmitted across optical fibers. The transceivers consume around 60% of the network power, and the remaining is coming from the electrical switches. On the transceiver front, a big part of the challenge comes from the fact that we are wasting a lot of energy moving data from the switching ASICs to the pluggable transceivers that are at the edge of the switch front panel. And so there's been a lot of work over the past decade in the research community on how we could move the optics much closer to the switching ASIC so that they ideally sit on the same package, and really optimizing the underlying optical components. And on this front, at MSR, we've actually worked with partners to design optimized modulators and photodetectors that have the potential to reduce transceiver power by an order of magnitude. And in general, this notion of optical co-packaging is getting a lot of traction in industry, which is great because it addresses this blue piece of the pie. However, this in turn converts the switching power into the next bottleneck. And an obvious question to ask is, what do we do about this green elephant in the room? As I mentioned, historically, we relied on electrical switches that have scaled in line with Moore's Law. But that trend is becoming harder and harder to sustain. So effectively, we have a mainstream technology that is approaching the tail end of its S-curve. And the question we are asking is, are there other non-CMOS based technologies that could lead to new growth curves for the future of our cloud network? And on this front, optics has a lot of potential. Actually, as it turns out, there's been more than 20 years of research in the optics and physics community on different physical layer technologies that can essentially switch light waves at fast granularity. The particular technology we took a bet on is actually very simple. The core of a network is just a passive diffraction grating. No moving parts, no electricity. It's just a piece of glass with etchings on it, and it behaves like a prism. So if we send our data on the red wavelength, it goes in one direction. If we send it on the green wavelength, it goes in a different direction. So we can use this as a switching block in our data centers as long as we have a light source whose wavelength we can control, which is precisely what a tunable laser lets us do. Now, in order to support cloud workloads that can be very bursty and may require almost packet by packet switching, we need these lasers to be tuned at nanosecond granularity. Unfortunately, when we started this project back in 2016, 2017, the off-the-shelf tunable lasers we were using could only be tuned at millisecond granularity. So that was 6 or so orders of magnitude off. And that's when the penny dropped for us. In order to make this technology viable for prime time, we actually have to innovate at the physical layer, which is different from the traditional research we've done at Microsoft and Microsoft Research. So we took the dive, we designed our own custom optical chips, and you can see them on the screen here. They're tiny chips that can achieve this laser tuning in less than a nanosecond. So in this process, we designed our own chips. We got them fabricated at external foundries. We were able to test them at die levels. We got them packaged. And while this was a great learning experience, it was only the very first step of a very long journey, resulting in an end-to-end demonstration of a system prototype where we were able to transmit real data between endpoints. And we were able to demonstrate the end-to-end reconfiguration latency of less than 4 nanoseconds. And this is neat because we are showing the viability of a system that can be reconfigured at packet by packet basis while relying on our optical technology. Now, as you can imagine, achieving this required going beyond our custom chip and solving the associated physical layer challenges. We had to solve challenges across the entire data center network stack. For example, we designed and implemented a time synchronization protocol that can achieve synchronization at a granularity of less than a nanosecond, yes, yet it's scalable and very robust. Similarly, we had to solve the long-standing problem of scheduling in an optically switched network, whereby coming up with a scheduler that can operate at nanosecond timescales, yet is practical to deploy, is incredibly hard. And the thing I want to point out is that these are not new technical problems. These are well known in different communities. I have a networking background, and we love designing scheduling algorithms and congestion control protocols. That's our bread and butter. But because we've gone after these problems in a piecemeal fashion, the general prognosis regarding the viability of optical switching has been pessimistic. And the only reason we were able to come up with a slightly more optimistic outlook is because we went after these problems in a cross-layer fashion. And we really tried to co-design a solution with the idiosyncrasies of the cloud environment and our cloud workloads. And that's one of the joys of working at Microsoft Research. Our team here has computer scientists and physicists and optical experts and chip designers and mechanical engineers working hand in hand to reimagine cloud infrastructure given the cloud context. And that's the message I want to leave with you. We have this emerging tsunami of emerging scenarios like resource disaggregation and machine learning that are going to put a lot of pressure on the underlying network at the same time when mainstream networking technologies are starting to run out of steam. We are betting on optical innovation, which will allow us to create new forms of transceivers and new kinds of switching technologies, which hold the promise of offering that step change in network performance that we are looking for. And the key insight here is to co-design these solutions across the entire data center stack and with cloud applications in mind. And this co-design exercise is not just a one-way street that benefits the network. It has implications for future cloud applications too. For example, Imagine designing a distributed system or an AI training chip that can assume that the underlying cloud network is completely synchronous. It can have massive implications for cloud application design. And that's the opportunity that I want you to think about. So I'm going to stop here. Thank you for your time. Hope you have a lovely research summit. And if you'd like to more about this work, I'd love to tell you more. Thank you again.